Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue further in our series on natural products and spectroscopy. Dear friends, in our previous session we discussed on carbohydrates in detail, and today also we are going to give you in-depth knowledge on the same topic, that is carbohydrates. Friends, for the discussion on the topic we have with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dal Singh College, University of Delhi. Dr. Vandana has immense experience and immense knowledge, and we are going to take advantages from her experiences today. If you wish to ask questions on today's topic from Dr. Vandana, then do call us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. You are requested to call in the last 10 minutes of the lecture so that first you get in-depth knowledge on the topic first. Now I would like to welcome our guest, Dr. Vandana, once again. Hello ma'am, welcome to the lecture.
Thank you so much ma'am. Hello viewers. We were discussing about the natural products and spectroscopy, and in this series we have started a new topic, that is carbohydrates, and today we are discussing about the second part of carbohydrates. In the last lecture we have discussed about the introduction part of carbohydrates, that is what are actually carbohydrates, what is the significant role in our daily life, what is the classification of carbohydrates, and in that series we have taken first compound, that is glucose. We have discussed about the chemical properties, reactions about glucose. In that portion we have discussed about the open chain structure of glucose, the important reactions given by glucose. We have discussed also how can we configure the alpha D or beta D glucose, pyranose structure and furanose structure of glucose, and we have also discussed about the conformation of cyclic structure, that is hemiacetal structure of glucose. In today's lecture, let us have a first what were the carbohydrates. You know, carbohydrates we have discussed in last lecture that it are nothing but initially we said that these are the hydrates of carbon, and you can say CXH2OY. Simple carbohydrates are also known as sugars or saccharides. We have sucrose for ordinary table sugar, glucose for the principal sugar in blood, fructose. These are the examples of carbohydrates we have discussed in last lecture. Later on we have discussed another definition of carbohydrates, that is these are the polyhydroxyaldehydes or ketones, or we can say those compounds which gives these compounds on hydrolysis, right? And so what are the carbohydrates? They contain carbonyl groups, hydroxyl groups, and they are also called, later we have described as hemiacetals or acetals. So carbohydrates that undergo hydrolysis to produce, about classification, only two molecules of monosaccharides, we called them disaccharides. Examples were maltose and sucrose. Then we have discussed about their hydrolysis part also. About oligosaccharides, what are oligosaccharides? These are the carbohydrates which contains monosaccharides 2 to 10 units. About polysaccharides, carbohydrates which contains more than 10 monosaccharides were known as polysaccharides. So these were about the classification part about carbohydrates. Now let us take new topic for carbohydrates. This is mutarotation. Little bit about mutarotation you have heard in the last lecture. Let us discuss in detail what is mutarotation. Cyclic hemiacetal structure of D-glucose comes from experiment in which both alpha and beta have been isolated. Ordinary plus glucose has a melting point of 146 degrees Celsius. You know, we have discussed in detail what is the difference between relative configuration and absolute configuration. As far as relative configuration, that is capital D and capital L is concerned, capital D full form is DE, that is DE. For full form of capital L, it is LAL. As far as the full form of another absolute configuration, that is D and small d and small l. Small d means dextro, small l means levo. That is, if a carbon compound, chiral carbon compound is in molecule, it has definitely has either D or S configuration. That is, if we apply chiral rule on carbon atom, all the atoms, 4 different atoms or groups attached to the carbon atoms must be in a either it is a D, dextrorotatory or levorotatory. And what about capital D and capital L? If the hydroxyl group in a carbohydrate or in a monosaccharide resides on last asymmetric carbon atom on right hand side, it will be named as capital D. And if hydroxyl group in a monosaccharide on last asymmetric carbon atom lies on left hand side, it will be named as capital L, that is L sugars. So this is nothing, this capital D shows the relative configuration, this plus shows the dextro, that is the absolute configuration of glucose. Whenever you write the monosaccharide or carbohydrate, you need to write these things. However, as far as mutarotation, however, when D plus glucose is crystallized by evaporating an aqueous solution kept above 98 degrees Celsius, a second form of D plus glucose with a melting point 150 degrees Celsius, that is a form which is having a different melting point, can be obtained. How it obtained? When the optical rotation of these two forms are measured, they are found to be significantly different. But when an aqueous solution either form is allowed to stand, its rotation changes, optical rotation changes from one form to another form, or we can say from one range to another range. The specific rotation of one form decreases and the rotation of other increases till both solutions show the same value. A solution of ordinary D plus glucose with melting point 146 degrees Celsius has an initial specific rotation of plus 112 degree, but the specific rotation of this solution falls to plus 52.7. You are observing here that the value decreases. A solution of second form of D-glucose with melting point 150 degrees Celsius has an initial specific rotation of plus 18.7 degree, but slowly the specific rotation of this solution rises or increases to 52.7. So you can see one value decreases and one value increases. The change in rotation towards an equilibrium value is called mutarotation. The explanation for this mutarotation lies in the existence of an equilibrium between the open chain form of D-glucose and the alpha and beta forms. You are hearing new forms, alpha and beta forms of the cyclic hemiacetals of glucose. And here you can see graphical representation. This is what you can see, the chair form of glucopyranose. If you see this, the position of this hydroxyl group, it is axial, it is alpha D plus glucopyranose, and if you can see all the group attached in this chair form of a glucose, only this is different from this, rest are the same. So it is nothing but it is a equatorial hydroxyl group, and it is nothing but it is beta D plus glucopyranose, because this structure resembles in pyran, so we can say beta D glucopyranose. And look carefully, the melting points of both the forms have different values. Alpha has 146 degrees Celsius while beta has 150 degrees Celsius. Another point need to observe over here is that the specific rotation 25 degrees Celsius for this alpha is plus 112 degree, and for beta it is plus 18.7, and you can see these forms are interchangeable to each other via open chain structure of D plus glucose. So this is alpha D glucopyranose, this is beta D glucopyranose, both are in interchangeable with each other via open chain structure. You can see this is nothing but open chain structure of D glucose, right. So this is called mutarotation, the change of one form to another form via open chain structure. Here you can see the specific rotation gets changes from this value to this value, and moreover, if you remember, I showed you that the open chain structure has a specific rotation 52.7 degree, So, this open chain structure has 52.7. At equilibrium, small amount of open chain structure of glucose also found. X-ray analysis has confirmed that ordinary D-glucose has the alpha configuration at the anomeric carbon. What are anomeric carbon? This carbon, the attachment of this group, the position of these two are different. So, these are anomers, alpha and beta glucopyranose, and this carbon is called anomeric carbon. The higher melting point has the beta configuration. The concentration of open chain D plus glucose in solution at equilibrium is very small. You must notice this, the amount of D glucose is very small. Solution of D plus glucose gives no observable UV or IR absorption band. If you have seen our lectures on spectroscopy, I have discussed about ultraviolet visible spectroscopy in detail and infrared spectroscopy in detail, in which we have discussed how these techniques helps us to elucidate or to determine the structure of an unknown compound. So, the solution of D-glucose gives no observable UV or IR. So, no significant peaks are there for D plus glucose for a carbonyl group, and the solution of D plus glucose gives a negative test with the Schiff's reagent, a special reagent that requires a relatively high concentration of a free aldehyde group rather than a hemiacetal in order to give a positive test. So, if a compound is having carbonyl group in its structure, it must give positive test with Schiff reagent, and when it is not giving Schiff positive test with Schiff reagent, something is different is there, that is we can say hemiacetal structure is there. We have discussed in detail about the hemiacetal structure of glucose in last lecture. It is convenient at times to represent the cyclic structures of a monosaccharide without specifying whether the configuration of anomeric carbon atom is alpha or beta. You can represent like this. This is like wave type. This bond is wave type, and you can see here. So, it can represent either in this way, that is in this way, chair form or flat hexagon. So, both are correct. You can represent either in this way, alpha or beta, because this bond you have represented a wave representation, and this one. So, we can represent glucose in either of this way. The beta anomer of a pyranose is not always the more stable. However, with the D-mannose, the equilibrium favors the alpha anomer, and this result is called an anomeric effect. You can see over here, what is this? This is alpha D mannopyranose, right? And this is another structure. This is beta D mannopyranose, and you can see the percentage amount at equilibrium for both the structure. This is 69 and this is 31. Now, mechanism part, the phenomena of mutarotation indicates that the two forms of D-glucose, we are talking about alpha and beta, are interconvertible and they have a common intermediate, that is open chain structure. This changes takes place via the open chain structure. The generally accepted mechanism is virtually the same as described for the acid and base catalyzed hemiacetal and hemiketal formation of aldehyde and ketones. If you remember, while discussing about aldehyde and ketones, we have discussed in detail how can we form acetal and hemiacetal or hemiketal or ketals from aldehydes and ketone. Let us see in this also, in this case also. This is acid catalyzed hemiacetal formation. What is acid catalyzed? In presence of acid. You can see this is a acetaldehyde. We are reminding it again, and you can see first of all this electronegative also accepts this proton and will give you this oxonium ion, right? And then this CH3OH will, this oxygen attack to this electrophilic carbon, because this positive charge attracts the shared pair of electron towards itself. So, this carbon become electrophilic in nature, and this oxygen can easily attack on this carbon, and you will get this kind of intermediate. And this is the another step. As far as positive charge is on oxygen atom, it immediately attracts these electrons towards itself, and you will get hemiacetal. So, this is what? This is the mechanism of acid catalyze how to form hemiacetal from an aldehyde. This is base catalyzed hemiacetal formation. Here you can see first of all what happens. This base OH attack to this, it will create this kind of anion methoxide, and it will attack to this electrophilic carbon, carbonyl carbon, and you will get this kind of intermediate. Because of the electronegativity difference, these bonded electrons get shifted towards the more electronegative atom, that is oxygen atom, and this carbon become electrophilic in nature, that is it will acquire a positive charge. As soon as it acquires a positive charge, this will attack to this electrophilic carbon. So, you will get this kind of intermediate, tetrahedral intermediate. Now, on hydrolysis it will give you hemiacetal, right. So, these two acid catalyzed and base catalyzed hemiacetal formation is there. Let us see in case of glucose. When mutarotation takes place, the ring of one forms opens up and then recloses in the inverted position to give the second form, that is beta form. We are talking about second form. What is that? Beta form. You can see this is what? Nothing but it is a alpha anomer of glucose, alpha D glucopyranose. And here you can see this is Ha means acid and this is B negative, this is base. So, you can do in either way as we have discussed in earlier slides, in acid catalyzed hemiacetal formation or base catalyzed hemiacetal formation. And how it took place, you can see over here, the ring gets open from here, right, and you will get this kind of structure. This is open chain form and you will get this kind of beta anomer, right. The very important next reaction is glucoside formation. When a small amount of gaseous hydrogen chloride is passed into a solution of D plus glucose in methanol, a reaction takes place that results in the formation of anomeric methyl acetals. What is anomeric? That is a methyl. This group is introduced, this methyl group is introduced at this carbon, anomeric carbon. We were talk about in the last slide alpha and beta. How it took place, you can see over here, this is what? This is a open chain structure of D-glucose and it is in equilibrium with this kind of, it is we can say a alpha or beta, and when it reacts with methyl hydroxide in presence of HCl, you will get this kind of a structure. You can see this hydroxyl group get replaced by this methoxy group and this is called methyl alpha D glucopyranoside. And look at the melting points and specific rotation for this particular isomer. This is 165 and specific rotation is plus 158. For beta, you can see the melting point is different from this. It is a lower melting point with respect to this alpha, it is 107 degrees Celsius and a specific rotation is minus 33 degree. Carbohydrates acetals are called glycosides and acetal of glucose is called glucoside. Glycosides general name and for glucose it will be glucoside. Acetals of mannose are mannosides, acetals of fructose are fructosides, and you can name in a same way and you can say so on. The methyl D glucosides have been shown to have 6 membered rings. So, they are properly named what, how can we? Methyl alpha D glucopyranoside and methyl beta D glucopyranoside. Here is the mechanism for the formation of methyl glucoside. How it happens? First of all, you can see this is nothing but this is, you can see the hydroxyl position in this chair form. So, this is nothing but equatorial position. So, it is beta D glucopyranose. In presence of acid, what happens first? This proton will attach to this hydroxyl group, or we can say protonated water molecule is there. As soon as this protonated water molecule is formed over here, it get attracted by this, and you can see like this kind of, what happens when removal of water take place from here? This kind of moiety is here, oxygen with positive charge, because it has donated its lone pair of electron to this bond. So, here is now a double bond and this oxygen acquire a positive charge. As it acquires a positive charge, this CH3OH right, methyl alcohol, it will attack to this. How it attacks? Anomeric carbon. This is what? This is a anomeric carbon. It was, now it is not, but it was anomeric carbon, and attack by oxygen on either face of the resonance stabilized carbocation, right. So it can attack in two way, in this side and this side, both side it can attack, and you will get these kind of structure by attachment of these, and by the you can see by the attack of this base A negative, you will get this kind of a structure. So this is the mechanism how it takes place. You can see this proton get abstracted by base. Here also you can see this proton get abstracted from here. So you will get what? Methyl beta D glucopyranoside and methyl alpha D glucopyranoside. So hope you understand this, how the methyl glucosides are formed by the attack in the presence of acid or in presence of methyl alcohol. Electron pair of the adjacent oxygen atom, it is talking about for this oxygen, stabilize the carbocation, right, that forms in this second step. It is talking about this statement is about this. Glycosides are stable in basic solutions because they are acetals. In acidic solutions, glycosides undergo hydrolysis and produced a sugar along with the alcohol. The alcohol obtained by hydrolysis of a glycoside is known as an aglycone, and here you can see this is glycoside of glucose. Glycoside comes from glucose, and here you can see it shows the alpha or beta, either it is a beta or alpha, and we have taught you about that it is stable in basic solution, but as far as acidic solution is concerned, it undergoes hydrolysis. So this alkoxy group, OR group, gets changes to hydroxyl group. It is nothing but aglycone along with the alcohol ROH. When an aqueous solution of methyl beta D-glucopyranoside is made acidic, we are taking it arbitrarily, not very specifically. Methyl beta D-glucopyranoside is made acidic. The glycoside undergo hydrolysis to produce D-glucose as a mixture of the two pyranose forms, and in equilibrium with a small amount of open chain also is there. Here you can see this is the structure of methyl beta D-glucopyranoside, because methyl group is there in spite of H. So this is glucopyranoside, and you can see this is the protonated water molecule. With the presence of this protonated water molecule, what happens? This kind of a structure you will get, because this proton get attracted by this electron pair of oxygen. As far as it attacks to this oxygen acquire a positive charge, and when this oxygen acquires a positive charge, you can see the adjacent bonded electron get attracted to this oxygen positive atom, and as it attracted toward this oxygen, consequently the lone pair of electron of this oxygen atom get attracted by, or we can say shifted to this. So you will get this kind of a structure. Here you can see this single bond get doubled, right, and this oxygen, because it already donates its lone pair of electron to this bond, now it leaves a positive charge, right, because electrons pair get away from this oxygen, so it leaves a positive charge over here. Now what happens? This can attracted from this side or from this side. So there are two possibility. One is this, one is this, and you can see what happens thereafter on hydrolysis. You can see this is water molecule. This proton get attracted by this oxygen atom, and you will get beta D glucopyranose or alpha D glucopyranose from alpha intermediate, and from beta you will get beta D glucopyranose, right. Many naturally occurring compounds are glycosides. Here you can see this is an example. You can see this is what? A glycon, and this is a carbohydrate structure, and you as a whole it is a salicin. An example is salicin glycosides, a compound found in the bark of willow trees as early as the time of ancient Greeks, preparations made from willow bark were used in relieving pain. Eventually, chemists isolated salicin from other plant materials and were able to show that it was responsible for the analgesic effect of the willow bark preparations. Salicin can be converted to salicylic acid, which in turn can be converted into the most widely used modern analgesic, that is aspirin. This is another important reaction is there. We can say Lebri-de-Bruyn-Elberda-Van-Ekenston transformation. And when we talk about this reaction, it involves enolization, it involves tautomerization, and it will also involve isomerization. So, what is this Lebri-de-Bruyn-Elberda-Van-Ekenston transformation? Dissolving monosaccharide in aqueous base causes them to undergo enolization and a series of keto-enol tautomerization, and that lead to isomerizations. For example, if a solution of D-glucose containing calcium hydroxide is allowed to stand for several days, several products can be isolated, including D-fructose and D-mannose. And this is a very important reaction, and it is known as Lebri-de-Bruyn-Elberda-Van-Ekenston transformation after two Dutch chemists who discovered it in 1895. Lebri-de-Bruyn and Elberda-Van-Ekenston. These are two Dutch scientists, and you can see here how this transformation, we can say tautomerization, enolization, isomerization take place. What we were talking about this, you can see hydroxyl group is there, aqueous, and this is the open chain structure of D-glucose. What happens first of all? This hydroxyl group abstract this proton from here, and it leaves a carbon ion, and this is in rearrangement takes place over here, and isomerization takes place here, and you get another kind of isomer like this. How it took place? This electron get shifted to this, and these bonded pi electrons get shifted to this carbonyl oxygen, that is more electronegative as compared to carbon. So, it will acquire a negative charge, and this single bond get doubled. So, these are the isomers, these are enolate ion. And on hydrolysis, what happens? You get D-mannose. This is one reaction. Another reaction can take place also. Here you can see what happens here. You will get what? En-diol. So, this kind of a structure is also here. A proton from it can attach to this oxygen. So, you will get en-diol. Diol is there OH at adjacent carbon. So, we can say en-diol. And one more structure is here. What you can see over here, this it is called tautomerization. Proton get shifted from this carbon to this, from this carbon to adjacent carbon. Here you can see this is a when we started, it has a aldehyde group at terminal end, it was a glucose, and here you can see there is a ketonic group at carbon number 2. So, it is nothing, if you remember, it is D-fructose. So, you can say what an important reaction is there. You have in a same reaction D-glucose, you have enolate ion, you have D-mannose, you have en-diol, you have D-fructose. So, in this way, this reaction is very important. A single reaction involves enolization because enolates are there, tautomerization because tautomers are there, and isomerization and because isomers are also there. So, this is very important kind of reaction. When carrying out reaction with monosaccharide, it is usually important to prevent these isomerization. All the time we don't need these isomers. So, what we can do thereby to preserve the stereochemistry at all of the stereo centers. You know how to preserve the stereochemistry? One way to do this is to convert the monosaccharide to the methyl glycoside first. And you know how we can convert a monosaccharide to methyl glycoside? We have discussed just few minutes back. You can react the monosaccharide with methyl alcohol in acid form or in base form. We can then safely carry out reaction in basic media because the aldehyde group has converted to an acetals, and acetals are stable in aqueous base. So, you know how we discuss in this part, we have discussed about mutarotation. What is mutarotation? The Changes of alpha D-glucose to beta D-glucose via open chain structure. We have discussed a very important reaction, that is how we can form the glycosides. We have discussed about the very important reaction, that is Lobry-D-Brand Venn Ekiston reaction transformation, when numbers of isomers are there, tautomerization is there, enolization is there, isomerization is there. But how can we prevent? We have learned this also. So hope you understood this. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to be with us as we are back after a short break, and afterwards we are going to talk more on the carbohydrates. Thank you.
Thank you so much.
Hello friends, welcome back to this session. Friends, in this session also we are going to talk more on carbohydrates, and for the discussion of the topic we have with us in our studios Dr. Vandana. Dr. Vandana is a prolific and a dynamic professor who believes in giving her best to the students. Therefore, she makes constant and continuous efforts so that the student community is benefited as a whole. Friends, she is an assistant professor in Department of Chemistry, and she is teaching in the Al Singh College, University of Delhi. So if you have any queries regarding today's lecture, if you have any question regarding the topic that is carbohydrates, then you can contact us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. You are requested to call in the last 10 minutes. Now, I would like to welcome our guest, Dr. Vandana, once again.
Thank you so much, ma'am. Hello viewers, we were talking about in the last part mutarotation, that is beautiful phenomenon in carbohydrates, and we have discussed by taking the example of glucose how the mutarotation take place, that is how the alpha D-glucopyranose and beta D-glucopyranose get forms via open chain structure. Then we were discussing about the glycosidic reactions, then we were discussing about the tautomerization through Lobry-D-Brand Venn Ekiston transformation reaction. Let us discuss more about the carbohydrate, that is how can we form the ethers, formation of ethers. A methyl glucoside, we have discussed it, how can we form from glucose. A methyl glucoside can be converted to the pentamethyl derivative by treating it with dimethyl sulfate in aqueous sodium hydroxide. It is a multiple Williamson synthesis. The hydroxyl groups of monosaccharides are more acidic than those of the ordinary alcohols, because the monosaccharide contains so many electronegative oxygen atoms, all of which exert electron withdrawing inductive effect on nearby hydroxyl group. In aqueous NaOH, the hydroxyl groups are converted to alkoxide ions, and each of these reacts with dimethyl sulfate in an SN2 reaction, that is substitution nucleophilic bimolecular reaction, to yield a methyl ether. The process is called exhaustive methylation. How it took place? Let us see. This is what you can see. This is the methyl glycoside. It can represent alpha or beta form. And this hydroxyl group, what it does over here, it abstracts this proton, right? And you will get this kind of intermediate. And by the reaction of this dimethyl sulfate, you can see this is what? Dimethyl sulfate. You will get this kind of moiety. So you can see the methyl group is introduced over here, and we can introduce more methyl group over here, and over here. So you can see all the hydroxyl group gets changes to methyl derivative. So it is what? 1, 2, 3, 4, 5. So you can see this is pentamethyl derivative. The methoxy groups at C2, C3 and C4 and C6 of pentamethyl derivatives are ordinary ether groups. We were talking about these groups 1, 2, 3, 4, 5. We are not talking about this. Okay, so keep in mind we are not talking about this, we are talking about these 1, 2, 3, 4. These groups are stable in dilute aqueous acid, these groups. So cleavage of ethers require heating with concentrated HBr, this is hydrogen bromide or hydrogen iodide. The methoxy group at carbon number 1 however is different from the others because it is the part of acetal linkage. For now we are talking about this. This is carbon number 1. It will not cleavage easily, right? Therefore, treating the pentamethyl derivative with dilute aqueous causes hydrolysis of this glycosidic methoxy group and produces 2,3,4,6 tetra-O-methyl D-glucose. Here you can see on hydrolysis these groups C2, 3, 4 and this one get changes on hydrolysis, but it will not. So you can see 2, 3, 4, 6 tetra-O-methyl D-glucose. Notice in the open chain form that oxygen is at C5 does not bear a methyl group because it was originally a part of the cyclic hemiacetal. So you can see only hydrolysis of this group will take place and not on these carbon atoms. Conversions to esters. You know what are esters? RCOOR. Treating a monosaccharide with excess acetic anhydride. This is acetic anhydride. And a weak base, here you can see such as pyridine or sodium acetate, converts all of the hydroxyl groups including the anomeric hydroxyl group to the ester group. Ester group is what? R, C, O, O, R. You can see all the hydroxyl group gets converted to ester group. And if the reaction is carried out at low temperature, for example 0 degrees Celsius, the reactions occurs stereospecifically, means only alpha anomer gives the alpha acetate and beta anomer gives the beta acetate. Now conversion to cyclic acetals. Aldehydes and ketones react with open chain 1,2-diol to produce cyclic acetals. Here you can see this is the acetone, this is 1,2-diol and this is a kind of cyclic acetal. If the 1,2-diol is attached to a ring as an monosaccharide, formation of this cyclic acetal occurs only when the vicinal hydroxyl group, these are the vicinal hydroxyl groups, are cis to each other, they must be cis. For example, alpha D galactopyranose reacts with acetone in the following way. Here you can see this is the structure. Here you can see how the reaction takes place over here and over here. The formation of cyclic acetals can use to protect certain hydroxyl group of a sugar while reactions are carried out on other parts of the molecule. So we can protect these groups. If we don't want to have reaction of these hydroxyl group, first of all we need to make this cyclic acetals by reaction of this acetone, or you can say with sulfuric acid. So these acetals formed from acetones are called acetonides. Another reactions, important reactions of monosaccharide is oxidation reactions. A number of oxidizing agents are used to identify functional groups of carbohydrates in elucidating their structure and for synthesis. If you remember, when we are elucidating the structure of glucose, we were talking about a little bit in oxidation reaction of glucose. Let us discuss in detail about the oxidation reaction. The most important oxidizing agents are Benedict or Tollens reagent, bromine water, nitric acid and periodic acid. These are the oxidizing agents. Each of these reagents produces a different and a usually specific effect when it is allowed to react with monosaccharides. Let us see first Benedict or Tollens reagent, that is reducing sugars. What is this reducing sugar? We will discuss parallelly what are the reducing sugars or non-reducing sugars. Benedict reagent in alkaline solution, what is this? An alkaline solution containing a cupric citrate complex ion. And what is Tollens solution? Silver ammonical nitrate. These oxidizes with aldoses and ketoses. means these oxidizing agent get oxidizes with these aldoses and ketoses, and the tests are positive even though aldoses and ketoses exist primarily as cyclic hemiacetals. We know that aldoses and ketoses somehow exist in cyclic hemiacetal, not always in the open chain structure. Benedict solution and the related failing solution, what is failing? Which is contains a cupric tartrate complex and give a brick red precipitate of copper oxide, and when they oxidize in aldose, in alkaline solution ketoses are converted to aldoses, which are then oxidized by the cupric complexes. So, you know what is the role of oxidizing agent? To oxidize the aldehydes and ketone and get reduced themselves. So, we can see in that way that sugars that reduce this oxidizing agent are reducing sugars, and that the sugars which cannot reduce these oxidizing agent are non-reducing sugars. The solutions of cupric tartrates and citrates are blue and give the appearance of brick red precipitate with aldoses. Here you can see this is the Benedict solution, which is blue in color when it reacts with aldoses, and or we can say when it oxidizes aldose, you will get what? A precipitate of copper oxide and other oxidation products, right? It can also react with ketones also, and the reaction will be same. And how can you analyze whether the reaction took place or not? How can you analyze? You will have a brick red reduction product. Sugars that give positive test with Tollens or Benedict solution are known as reducing sugars, right? And all the carbohydrates that contains a hemiacetal group will give positive test. So, it is very significant, very important statement. I want to repeat it again. All the carbohydrates that contain a hemiacetal group will give a positive test. So, what is the condition for a carbohydrate to be a reducing sugar or to give the positive test? In another way, we can say what are the carbohydrates which give positive test? That must have a hemiacetal group in their structure. In aqueous solution, these hemiacetals exist in equilibrium with relatively small but not insignificant concentrations of non-cyclic aldehydes, or we can say open chain structure or alpha hydroxy ketones. In case of fructose, it is the latter two that undergo the oxidation, perturbing the equilibrium to produce more aldehyde or alpha hydroxy ketone, which then undergo oxidation until one reactant is exhausted. Carbohydrates that contain only acetal groups do not give positive test with Benedict or Tollens solution. They are called non-reducing sugars. Acetals do not exist in equilibrium with aldehydes or alpha hydroxy ketone in the basic aqueous media of the test reagent. So, here we can represent in this way what are the reducing sugars, what are the non-reducing sugars. Here you can say this is the acetal structure, or we can say hemiacetal, where this R dash is H, or it can be a CH2OH, and it will give a positive test with all the oxidizing agent, and it will not give the positive test. That is, we are talking about the non-reducing sugars. These are acetals, and R dash group can be H and CH2OH. Here you can say what is the difference? This H get replaced by this alkyl group or another sugar. Although Benedict's or Tollens reagents have some use as a diagnostic tools, Benedict's solution can be used in quantitative determinations of reducing sugars reported as glucose in blood or urine. Neither of these reagents is useful as a preparative reagent in carbohydrate oxidations. Oxidations with both reagents take place in alkaline solution, and in alkaline solutions sugars undergo a complex series of reactions that lead to isomerization. That is why we are not using this for this particular purpose, that is for oxidations, because of isomerization is there. Now, this is bromine water oxidation with bromine water. What happens over here? Synthesis of aldonic acid took place. Monosaccharides do not undergo isomerization and fragmentation reaction in mildly acidic solutions. Thus, a useful oxidizing reagent for preparative purposes is bromine in water. Bromine water is a general reagent that selectively oxidizes only the aldehyde group to the carboxylic group. It converts an aldose to an aldonic acid. You know what is aldose? A carbohydrate that contains an aldehyde group. Here you can see the master reaction. It's represent a aldose, and this represent the reagents, bromine, water, and this is a aldonic acid. Here you can see what? Only aldehyde group get converted to carboxylic group. Only aldehyde group get oxidized to carboxylic group. Bromine water specifically oxidizes the beta anomer, and the initial product that forms is delta aldonolactone. Right. This compound may then hydrolyze to an aldonic acid, and an aldonic acid may undergo a subsequent ring closure to form a gamma aldonolactone. How it took place you can see over here. This is beta D glucopyranose. Because of this, hydroxyl group is in equatorial position, and with bromine water oxidization takes place over here, and you will get this beta gluconolactone, and on hydrolysis you will get this beta D gluconic acid. This is beta D gluconic acid because carboxylic group is there, and you will get, by removal this water molecule, you will get beta D gluconic gamma lactone, cyclic ketone. What is lactone? Cyclic ketone. Another important oxidation is there, that is with nitric acid. What happens over here? Here aldaric acid will produce. You can see with dilute nitric acid is stronger oxidizing agent, then bromine water oxidizes both the aldehyde group and the terminal this CH2OH group of an aldose to carboxylic groups, and these dicarboxylic acids are known as aldaric acids. Here you can see this is a aldose, and with nitric acid, so what is the difference? With bromine water you will get the oxidation of aldehyde group takes place, and with HNO3 both group get oxidizes to carboxylic group. It is not known whether a lactone is an intermediate in the oxidation of an aldose to an aldaric acid. However, aldaric acid form delta and gamma readily. How it takes place you can see over here. This is aldaric acid when both the terminal groups are carboxylic acid, and they are certainly obtained from an aldohexose, and with the removal of water molecule, how the lactone takes place, or we can simply heat it and you will get this kind of lactone, gamma lactones of an aldaric acid, and corners such as do not represent a CH2 group. We are talking about these. We are just representing it. You can make a circle also, not the corners. And this is the D-glucose, right? You can see this is the open chain structure, a oxygen molecule must be here, and on nitric acid oxidation you will get D-glucaric acid. So how it forms you can see here in the case of glucose. Another important oxidation reaction are there, periodate oxidation. Oxidative cleavage of polyhydroxy compounds. Compounds that have hydroxyl groups on adjacent atoms undergo oxidative cleavage when they are treated with aqueous periodic acid, that is HiO4. And what happens over here? The reaction breaks carbon-carbon bonds and produces carbonyl compounds. The compounds carbonyl can be aldehydes, can be ketones, can be acids, and this is the representation of reaction. Here you can see this bond, this cleavage between carbon-carbon took place with the help of periodic acid, that is HiO4, and it represents, that is periodic acid, this is HiO3, H2O, and you can see over here we are not representing these, so carbonyl compounds can be there. What are the possibilities? Let us see in another slide. Since the reaction usually takes place in quantitative yield, valuable information can often be gained by measuring the number of molar equivalents of periodic acid that is consumed in the reaction, as well as by identifying the carbonyl products. So you can easily estimate it quantitatively. Periodic oxidations are thought to take place through a cyclic intermediate. So let us see the mechanism, how it took place, how the carbonyl group get produced with this. You can see this is the iodate ion IO4 negative, and this kind of pentacyclic, here you can see this I-O-O-O, and how it took place, how the bond cleavage took place, you can see over here. Notice in these periodic oxidation that for every carbon-carbon bond broken and a carbon-oxygen bond is formed at each carbon. Here you can see every bond is broken and 2 carbonyl, every bond is broken. When 3 or more CHOH groups are contiguous, the internal ones are obtained as formic acid. Periodic oxidation of glycerol, for example, gives 2 molar equivalents of formaldehyde and 1 molar equivalent of formic acid. Let us see it. It is a glycerol. Here you can see there are 3 CHOH, CHOH, CHOH. So this kind of cleavage at both the bond, that is this carbon-carbon and these carbon-carbon took place, and what you will get CHOH, HCOH, sorry, this is formaldehyde, this is formic acid, and this is another molecule of formaldehyde. So you can easily observe. Oxidative cleavage also takes place when an hydroxyl group is adjacent to the carbonyl group of an aldehyde or ketone, but not that of an acid or an ester. Glyceraldehyde yields 2 molar equivalents of formic acid, 1 molar equivalents of formaldehyde, while dihydroxyacetone gives 2 molar equivalents of formaldehyde and 1 molar equivalents of carbon dioxide. So you can see over here the difference. This is the glyceraldehyde, and you can see how the cleavage took place. This one, and this is the formic acid, this is another molecule of formic acid, and this is formaldehyde. This is what? Dihydroxyacetone. And how the cleavage took place from here, so you can get a formaldehyde, carbon dioxide molecule and formaldehyde. Periodic acid does not cleave compounds in which hydroxyl groups are separated by this CH2 intervening group, CH2, right. So you can easily differentiate the groups. And note those in which a hydroxyl group is adjacent to an ether or acetal function. Let us see first case. There is no cleavage, and this is the another case. We are talking about ether and no cleavage took place. So we can distinguish these compounds from there with the help of oxidation with periodic acid. Now another important reaction is there. So we have discussed oxidation in detail. With bromine water, you can see only aldehyde group or terminal aldehyde group get oxidized to carboxylic acid. In case of nitric acid, it is a strong oxidizing agent, so it will oxidize both the group, terminal aldehyde group and terminal CH2OH group. With the case of periodic acid, you have seen that with the help of periodic acid, cleavage, carbon-carbon cleavage took place, and we have seen also the different products with the help of periodic acid. Let us discuss in detail about the reduction. You know what is reduction? Addition of hydrogen. Simply we can say there are other definitions also, but what we can consider over here, the addition of hydrogen atom. Here we are discussing about the reduction of monosaccharides, and what are the products. In general we can say alditose, right. Aldoses and ketoses can be reduced with sodium borohydrate, that is NaBH4, to compounds called alditose. So this is the general reaction. It can represent a aldose, and here you can say these are the reducing agent, NaBH4 or hydrogen with platinum, and this is the product. What happens over here? This aldehyde group gets changes to CH2OS. Reduction of D-glucose, for example, yields D-glucitol. In general we can say alditol for carbohydrates, but for glucose we can say precisely D-glucitol. So this is this chain structure of glucose. This is the open chain structure of glucose, and this shows the reduction, and you can see the structure, the open chain structure of D-glucitol, the expanded structure of D-glucitol, or we can also say D-sorbitol. Now the another important reaction for carbohydrate is there, that is Kiliani-Fischer synthesis. What is that? Let us see first of all preview. In 1885, Heinrich Kiliani, this is Freiburg, Germany, discovered that an aldose can be converted to the epimeric aldonic acids having an additional carbon. Note it down, an additional carbon through the addition of hydrogen cyanide and subsequent hydrolysis of epimeric cyanohydrins. Fischer later extended this method by showing that aldonolactones obtained from the aldonic acid can be reduced to aldoses. The method of lengthening the carbon atom means we have to increase the carbon chain by one carbon of an aldose is called Kiliani-Fischer synthesis. It helps a lot. Fischer have take a lot of effort from this reaction, helps from this reaction. Kiliani-Fischer synthesis for D-glucose and for D-threose and D-erythrose from D-glyceraldehyde shows in figure. You can see in coming slide, addition of hydrogen cyanide to glyceraldehyde. If you remember, the aldehyde reaction produces two epimeric cyanohydrins because the reaction creates a new stereocenter. The cyanohydrins can be separated easily and each can be converted to an aldose through hydrolysis, acidification, lactonization and reduction with NaHG at pH of 3 to 5. One cyanohydrin ultimately yields D-erythrose and D-threose. What are these? Let us see. We can be sure that aldotetroses that we obtain from this Kiliani-Fischer synthesis are D sugars because the starting compound is D-glyceraldehyde and its stereocenter is unaffected by the synthesis. One of the bases, on the basis of Kiliani-Fischer synthesis, we cannot know just which aldotetroses has both hydroxyl group on the right and which has on left in the Fischer projection. However, we oxidize both aldotetroses to aldaric acid. One erythrose will yield an optically inactive, meso compound produced, while other D-threose will yield a product that is optically active. Let us see reaction in detail. Here is that this is a glyceraldehyde. It is having one carbon atom, one chiral carbon atom. You know what is chiral carbon atom? A carbon atom which has 4 different valencies satisfied with 4 different atoms or group. Right? What we are doing over here? First of all, we are reacting. This is overall a reaction. Let us see in more precise way. This is hydrogen cyanide. When it reacts to this glyceraldehyde, we have 2 stereocenters. One possibility is this, that hydroxyl groups are on the same side, and another possibility is this, that the hydroxyl groups are on opposite side. So we can say these are the epimeric cyanohydrins. When we are separated and then react with barium hydroxide and followed by hydrolysis, we get this kind of product, that is this cyano group get oxidizes to carboxylic group. And thereafter what happens? You will get this kind of lactone from that particular molecule and this kind of lactone from that particular. Here you can see the difference of hydroxyl group, nothing else. So you will get after reduction D-erythrose. What is erythrose? When hydroxyl group are on the same side, and D-threose when hydroxyl group are on opposite sides. So when you will do the oxidation part with the nitric acid or strong oxidizing agent, what happens? These terminal groups get oxidizes to carboxylic group in both cases. So you can identify which group is optically active. This group, after oxidation, when these groups are converted to carboxylic group, will be a optically inactive. That is, this will be a meso compound and it will be a optically active compound. So you have understood about the detailed reactions of oxidation reaction with bromine water, with nitric acid, with periodic acid. Then we have discussed about the reduction reaction, and we have seen in the last lecture how these oxidation and reduction reactions helps in identifying the configuration of structure of glucose. So hope you understood this lecture, and if you have any query you can mail me. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us this session on carbohydrates. Friends, you can post your feedback to us at info.cec@nic.in. We are going to meet again very soon and would be discussing more in our series on natural products and spectroscopy. Till then, take care. Goodbye. Thank you, ma'am.
Thank you so much.